And so please help me welcome to the stage Thorsten Jorokums.
Thank you. So I'm here both in my role as faculty member at Cornell as well as Amazon scholar working with Amazon Music, because in both roles, what I do is do research on learning from interaction logs. And what I mean by interaction logs, it's the logs from these systems that we're all collectively building and using. And ad placement systems, search engines, e-commerce sites, recommender systems, and more also systems that kind of interface with the physical worlds, like smart homes and self-driving cars. All of these systems log the interactions that our users have with them. And clearly, these logs contain a lot of interesting information because they reveal the preferences that our users have. But dealing with these logs is also tricky because our systems themselves bias the data that we're collecting. Now, but if we can get this bias out of the data, then these interaction logs are really a great source for measuring how our systems are doing, for learning and improving these systems, and for personalization. So let me walk you through a couple of examples what I mean by interaction logs. And they all have this structure that we have a context X, an action Y that our current system is taking, and then we observe some feedback delta. So for an ad placement system, like the one that we have here, the context may be the user and the page that we're dealing with. Our current system places a particular ad, like this Malaysia Airlines ad on the top right corner there. And then for that ad, we get to observe the feedback, whether the user clicks on it or not. But what we don't get to observe is the counterfactual outcomes. What would have happened if our current system had placed a different ad there? Right? We don't get to see whether the user would have clicked or not. Or think about a news recommender system, right? It puts together a personalized newspaper. Here, the context X is some user profile. Our current system takes an action Y, puts together this personalized front page, the selection of articles and the layout. And then for that particular page, we get to observe, let's say, the reading time, which we use as a proxy for user satisfaction. But again, we don't get to see what would have happened if we had put together a different front page here. Or our last example, a search engine. Here, the context X is a query. The action that the system is taking is presenting this particular ranking, and then we have some click metric, delta, that we want to optimize. But again, we don't get to see what would have happened if we had presented a different ranking. So in a sense, what we are getting here in machine learning terms is bandit feedback. These triples X, Y, and delta. But it's biased by the actions that our current system is taking, right? We only get to observe the feedback for the actions that we try. So nevertheless, what we want to do is we want to learn a new system, an improved system, a new ranking function, let's say, that selects actions Y with even better deltas. So how can we do this? That's the question that I want to address in this talk. If you think about it, what we're trying to do here is batch learning from bandit feedback, right? If you kind of partition machine learning into these 4 quadrants, we have online learning with interactive control, and batch learning where we're just learning from existing data. And we have full information feedback where we have like hand-labeled data and this bandit feedback. Then we are in that bottom right corner, right? And if you think about it, all of these other quadrants are very well supplied with machine learning methods. But what's happening in that bottom right corner? That's what I want to explore in this talk. And it's not that there isn't enough data. Actually, lots of data, terabytes of data, all of these logs files lie in that corner. OK, so what I want to do in this talk is first think about what is actually the problem and get at the heart of the problem. And I'm going to bring it down into what we call counterfactual risk minimization, which is a way of constructing learning algorithms for this particular setting, batch learning from bandit feedback. And then put this kind of theoretical framework into practice and show you 2 algorithms that we've developed. One for training conditional random fields called POEM, and the other one called BanditNet for training deep models based on this log data. OK, so where to start? Well, it's always a good idea to start and think, well, maybe you've solved problems that are kind of like that already. And then we can maybe adapt some of the methods that we have, right? And if I think about this setup of context X, action Y, and effect delta that we have in our online systems, well, it actually sounds a lot like what you would have in a medical treatment setting, right? So they would have a context X, which may be your patient, described by lab tests, let's say. Then you have to decide on a treatment Y. You take an action. And then for that particular treatment, maybe surgery, you get to see the outcome, right? And you want to improve the outcome. But again, you don't get to see what would have happened if you had given that person a different treatment, right? That's counterfactual outcomes are not observed. So how do we typically deal with these settings in the medical domain, right? And the gold standard there is to do causal inference via controlled randomized trials. Now, what I want to do in this talk is rethink what we're doing in online systems in terms of counterfactual and causal inference and controlled randomized trials. And clearly, many of the parallels break down, like, the action space in the medical domain is typically, just have a handful of different treatments, whereas in our cases, we have like combinatorial space of all rankings that are our treatments. But nevertheless, maybe we can adopt some of the ideas there. So let me just start by defining a couple of things. In particular, what do we want to learn? What we really want to learn is we want to learn a policy. And a policy is just a fancy word for a mapping pi that takes a context and says what to do, why, which action to take. And in particular, we'll think of stochastic policies for reasons which will become clear later. And so a policy is just a conditional probability distribution. Given a context X, draw actions from this distribution pi. If you want to visualize that, think of the gray box there as all the possible actions that we could take in our current context X. And then policy pi 1 would draw actions from that distribution, and policy pi 2 is a different policy, would draw actions from a different distribution. And clearly, deterministic policies are just a special case of this. You put all the probability mass on one of the actions, right? OK, so that's what we want to learn. How do we tell whether, how do we measure performance? And we'll do that in terms of utility, which is just the expectation of our feedback delta, the thing that we want to maximize or optimize. And so, again, if it's just computing this expectation here. If you do that in graphical terms, the policy pi 1, the shading indicates the value of our feedback, red being bad, green being good. And so like the policy pi 1 here would it takes mostly red actions, so it's not so good. The expectation is kind of reddish. And the policy pi 2 takes mostly green actions, so the expectation is greenish. It's better, right? So that's what we want to optimize. But unfortunately, it's just like prediction error, right? It's something we can't compute. Why can't we compute it? Well, the pi, the policy, that's not the problem, right? We built this. This is our system that we want to evaluate. So we actually know this, so that's not the problem. The p of x, yeah, that's our distribution of context, like users coming to our site. We don't exactly know that, but we can draw a large sample, so that's not a big problem either. The problem is that we don't know most of the deltas, right? We don't know the feedback for most of the context action pairs. So we have a lot of missing data. So what are we going to do? Well, the standard thing to do is to run an A/B test, right? Then we can estimate this utility. And A/B test just means we take our current policy, our current system, field it, give it to a random sample of our users. That's basically a controlled randomized trial, right? And then we just take the average of the deltas, and that's an unbiased estimate of the performance of our system, of the utility of the policy. This is great in terms of like causal validity, and both in medical settings and in the online system setting. That's kind of the gold standard for establishing how good a policy is, how good a system is, right? But unfortunately, in terms of efficiency, it's really bad, right? So what's happening here? If we actually have a lot of policies that we want to evaluate, then what we would need to do, we need to implement the policy, productionize it, field it in our system, and run it for at least a week to get, get rid of the cyclical nature of our data. And so if we do that for many different policies, that takes forever, right? This will give us a really low kind of turnaround cycle, development cycle. What we would much rather do is something like offline A/B testing, right? The online testing is also really wasteful. We collect the data once, and then we never use it again. So couldn't we just collect a whole bunch of data first? Actually, we already have that. We have terabytes of log data lying around, probably, right? Including the data from the old A/B tests. And then, using just the old data, evaluate a whole bunch of new policies, kind of in an offline A/B test. If we were able to do that, we could get turnaround times in seconds. And we could actually do learning, right? If we could do that for a lot of policies, we could basically use this as a form of training error that we could optimize. So what we want is we want counterfactual estimates of what would have happened, or what would have my performance been if I had used a different policy instead of the policy that actually collected the data, or by policy pi null. Sounds great, right? But what's the problem here? The problem is that we don't actually have the full data to do this, right? So in particular, the situation doesn't look like this, where we know the whole delta. But it more looks like this, right? In our data, in our log file, however big it is, we will only see some dots, right? Those are the actions that we've actually tried. But this, if we have a new policy pi that we want to evaluate, that when it wants to evaluate what the black action is like, chances are it's not in our sample, right? And we don't actually know what the delta, what the payoff for this action is. So the first thought that you may have is, well, let's build an imputation model. So let's go through that thought experiment and see what happens. So we could take all of our observed triples of data, embed them in some nice feature space, and then learn a regression model that would then be able, delta hat, that would then be able to impute the value of delta everywhere, right? So here, this is visualized again. We would learn our model, and now we can impute a value everywhere. So now, if we have a black action here that we just fill in the value of the predicted value from our regression model. Unfortunately, that can go horribly wrong, right? Especially if we are now optimizing over our model of the reward. It will tell us, oh, go into that bottom right corner there. That's where the kind of greenest area of the space is. So we're really at the mercy of how our model extrapolates. And here in this particular case, there's actually no data there. So we're really at the mercy of, if we have a mismatched model, the predictions there could be way off. So let's not go this route, because we get into biases that are difficult to control. Let's try something else. So the approach that we're actually going to use is going through a counterfactual estimator, and in particular, using inverse propensity score weighting, or IPS for short. And so IPS weighting just does the following. It looks a lot like what we have in an A/B test, but it weights the feedback delta by this ratio of what's the probability on the new policy that we want to evaluate, divided by what's called the propensity. And that's the probability of the action under the policy that logged the data. So again, to visualize that, pi null collected the data. Now we want to evaluate this other policy, pi. What this inverse propensity score, IPS estimator, does, it upweights the terms over on the right, and it downweights the observations on the left. And if you do it in this way, there's a 3-line proof that shows that this is an unbiased estimate of the online performance. So you get an estimate, you're estimating the same quantity that you would estimate in an online A/B test, but you're doing it by reusing old data. Now, one restriction here is, in the fine print, is this is only an unbiased estimate if the new policy is restricted to the actions that had non-zero probability under the logging policy pi null. So from that perspective, coming back to controlled randomized trials, it's actually beneficial to log your data with some kind of random behavior in it. And, well, the simplest way of getting randomness into your system is to simply make your logging policy a little bit random. And I'll show an example of how to do this on a later slide. But even if you're not doing this, your system probably is pretty random already. Like the features, X, that describe your contexts are probably somewhat random. You've run A/B tests, so the choice and the assignment of users to a policy is randomized. User behavior in your system is random. And maybe your system is actually a little bit flaky, and what was considered a bug before is now a feature, right? At least you would hope. So if you have a little bit of randomness in your system, you can exploit this, just like you would exploit this in a controlled randomized trial. So this gives us a way to run these offline A/B tests and get unbiased estimates. And that's our pathway. That's important for it in itself, right? You can actually use this to greatly speed up your development cycle. But it's also a pathway for doing learning. So what you can basically do is you can use this inverse propensity score estimator as a form of unbiased estimate of training error, right? And then you can do learning by minimizing training error or maximizing utility. So basically what you would do is you would find the policy that optimizes that estimated performance, just like most machine learning algorithms actually do. Empirical risk minimization. But you do have to be a little careful, because what can happen is the following. If you're searching a large policy space, then you can get into a particular new type of overfitting. So let's say the policy pi1 here that we're now evaluating against our log data is kind of close to the existing policy that logged the data. And so we will take an average over many kind of small weights. And so our estimate is going to be reasonably accurate in terms of variance. But we may have some policy in our policy space that's way up in the corner where we have very little data. And if you do inverse propensity score weighting there, it would basically put all of the weight on that one point. So we still have an unbiased estimate, but over one sample. So it's going to have huge variance. So you have to be careful about this. And if you look at kind of the learning theory behind these learning problems, then you can actually derive generalization error bounds that tell you that this is going on. So in particular, if you want to say something about the true utility, like the generalization error of the system, you have to look at the training error. You have the typical capacity overfitting, like VC dimension term in there. But you have this new term which kind of accounts for the variance of your estimator, and that is different for different policies. So you get an additional regularizer. Now, the numbers that come off these bounds are typically not that accurate, right? But these bounds do tell you what a learning algorithm should be optimizing. And so what we take away from that is this counterfactual risk minimization principle that tells you what your algorithm for batch learning from bandit feedback should be optimizing. And it's basically that you should be optimizing this objective, right? Optimize your training utility as measured by IPS. And you should account for variance regularization and for capacity regularization. So far for the theory. But can we actually take this and turn this into practical machine learning algorithms? So I'm going to give two examples for doing this. The first example is called Poem. And it's basically a way of training conditional random fields for structured prediction, but not on full information, hand-labeled data, but on data that we get from your log files, obviously much cheaper. So what do we need to do? Well, we have to define the policy space, the type of function that we want to learn. And I said we wanted to learn a conditional random field. And if you know what a conditional random field is, that's what it is, right? You have this kind of softmax function that's normalized to sum to 1 by this partition function z. And then you have a joint feature map phi of x and y that comes from your conditional random field. And then you want to learn this weight vector w. And that's the thing that you're adjusting in your learning algorithm. So you would take this and plug it into this counterfactual risk minimization objective. And then you basically plug this into the IPS estimator. As the capacity regularization, we use the typical L2 regularization that we have in a support vector machine or in a conditional random field typically. But then we have this additional variance regularization term, where you basically just have to look up an estimator for the variance there. I'm sweeping under the rug how to optimize this, but you can actually, with a couple of optimization tricks, you can do stochastic gradient descent on this, and you can do this large scale. So here's a sanity check, and kind of checking whether we can get the same performance training on log data that we get from full information data, kind of training a conditional random field in the traditional way. So we took a text classification data set where we had manual labels for a multi-label classification task. So we're predicting a bit vector, basically. Is it about sports? Is it about politics? So there's a bit vector that we're predicting. And then we train a conditional random field in the traditional way on this full information feedback, and that's our skyline. That's how good we could hope to possibly get. Now, from this full information data, we're now generating artificial bandit feedback data in the following way. We pick a document from the collection. We have a logging policy pi1. That's just a classifier. That's just a classifier. Our classifier makes a prediction. It says, oh, it's the correct label vector is 1010. And my propensity of making that prediction is 0.3. And then we observe what's the Hamming loss of this vector. So this basically means 2 bits are wrong. It doesn't tell you which ones, just that 2 are wrong. So this is this kind of contextual bandit feedback in the simulated environment. And then we give more and more of this contextual bandit feedback to our poem algorithm, now training a conditional random field, same structure of model, but trained based on this log data. And what you can see in the plot is we start in terms of the performance at our logging policy, which was pretty crummy. Lower is better. That's the red line up there. And then poem, if you give it more and more bandit feedback, it eventually approaches the performance of the skyline, right? That's how good we could hope to get. So that's a sanity check that we can actually do learning in this way from log data. So let's look at some real-world experiments here. So we've worked with a couple of companies trying this out on real systems. And I want to talk about one application here that we did with a large media company in New York City. They had the problem of, there was a particular kind of question answering type of problem where there was a query and they wanted to pick a high quality answer. And there was a kind of candidate set formation stage, which is a capital Y of X. And what they wanted to do is maximize the number of correct answers, roughly minus the number of incorrect answers. And we were allowed to be able to abstain. And that would be kind of a 0, right? You just abstain. So their existing system, they actually had collected some hand-labeled data, full information data, where somebody, editors had gone in and said, for this is the correct response. But it's actually really hard to do this because people typically, these editors don't know what the correct response is. Really only the user does, right? But they had this data. They trained a logistic regression scorer on this data. And then what they fielded was basically an argmax. So the action that had the highest score at prediction time, that's the thing that the system would present. And abstaining was one of the possible actions. Now, they weren't satisfied with the performance of this. So what we did is we stochastified this rule. And it's actually very simple in this case. We replace the argmax with a softmax. And so by putting this parameter lambda in there, we were able to control how stochastic our logging policy is. If you pick lambda to be very large, it's basically the argmax. If you pick lambda to be 0, it's the uniform distribution. And now you can tweak the lambda. And we tweaked it until the company was comfortable with the performance of the predictions that the system made, but where it was still sufficiently stochastic to give us reliable results from IPS estimation. Then we collected data from this stochastic logging policy, trained Poem, and came up with a new policy just using about 5,000 examples that gave us about a 30% improvement over the existing policy. And now we can iterate that, right? You can now field that policy, collect more data, retrain, and so on. So at that point, people typically ask, oh, can you also do deep learning with this? And the answer is yes. And really not that much changes, except for the optimization. So let me quickly talk also about BanditNet. But it's really almost the same, right? So instead of having this CRF model, where it's W times phi, we just plug a deep network in there. And in the following, we'll use a ResNet 20. But you could put any deep learning model that's differentiable in there. Then what you would do is you put this into your counterfactual risk minimization objective. Here we use slightly different estimators, but effectively, it's the same. And then if you do the same experiment, comparing the two ways of training the same ResNet 20, full information versus collecting bandit feedback in the same manner as we've done before. If you give it enough bandit feedback, the performance does converge to the performance of the skyline. So again, verifying that more generally, you can train basically any differentiable model this way. All right, so let me wrap up by stepping back a little bit and pointing out that this batch learning from bandit feedback is just one specific case of learning with partial information. In particular, if you're thinking about learning in a search engine, you probably wouldn't want to formulate that as batch learning from bandit feedback. And you may not be comfortable having a stochastic ranking function. But here you can actually exploit the stochasticity of your users. Your users are somewhat random. So what we come up with is actually methods for exploiting the randomness in user behavior and using that to debias the results and coming up with unbiased learning to rank algorithms. And as a side note, this whole framework about thinking about this as counterfactual inference and thinking about this as controlled randomized trials is also a really great way of thinking about bias in the sense of fairness of these systems. In particular, thinking about, is my policy fair to different constituencies, in particular the users of my systems, the people who type in the queries, but also to the items that are being ranked, where the items being ranked could be candidates for a job, for example, right? And last example of a partial information learning problem is matrix factorization. There again, you have a lot of missing data. People reveal some of their ratings, but they reveal it in a very biased way, right? They mostly reveal ratings that are 4 and 5 stars because they pick the movies that they think they will like, then they watch it, and then they rate them, right? So you have to deal that the missingness in this observation matrix is not completely at random. But if you model this, you can use the same kind of inverse propensity scoring techniques to tackle these problems as well. So to wrap up, what I wanted to make as a main point and the main takeaway here is that if you think about these systems from the point of counterfactual inference and in terms of controlled randomized trials, that opens up a new view of looking at this and gives you a new methodology to solve some of the bias problems that we have in these systems. In particular, it gives you this ability to do offline A/B testing, which can really speed up your development cycle. And it gives you the ability to do learning in these settings in an unbiased way. If you're interested in more of the technical details, there's a tutorial on my homepage from SIGIR 2 years ago that goes into a lot more detail. And you'll also find papers and software and data there. Thank you very much.
Thank you.